Rotation matrix. Now we know how to write down the rotation matrix. It is useful to consider two-dimensional rotation. It is very simple. Okay, I have x-axis and y-axis, and I would like to rotate a vector. A vector is expressed as a1, e1 hat plus a2, e2 hat. I'd like to rotate this vector. In this case, this is active transformation. If I rotate this vector by an angle of theta, for example, I have A, and if I rotate by this amount, theta, and I would like to find A prime in terms of original basis. That means after rotation, the relative direction, so relative to A E1 and A relative to E2 is the same as the A prime relative to E1 prime and A prime relative to E2 prime. So after rotation, I would get A1 prime, A2 prime. In this case, I do not change this. Or this is true, A1, E1 prime, A2, E2 prime. It is different from mathematical approach. Physics approach is this one, because I would, in mathematics, they fix this vector and change the basis. The coordinates also changes. In physics, I rotate this vector. So I need to find a prime that is a different vector. This one and this one, they are different. Different, however, in terms of the new basis, this is new basis that has been rotated by angle theta, the components are invariant. Instead, if I use these bases, then components varies. So we'd like to find the new values for this Cartesian components. Now we need to compute all of the directional cosines. That is the scalar product between scalar product of any two unit vectors. Relative to E1, we have E1 prime, we have angle theta. It is cosine, right? Relative to E1, we have E2 prime. E2 prime, they have a right angle plus a theta. Okay, so it should be cosine right angle plus theta. The result is, it is on the left side, so it is minus, and because 1/2 of pi, this is minus sine theta. Okay, then what's next? Next one is E2, 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 E2. It is theta relative to E2 prime, so it is a cosine. And then here, angle between E2 and E1 prime, it is 1/2 of pi minus theta. Therefore, it is a sine. Notice that we have negative sign. This guy is on the left side, so we have negative sign. But in here, this theta and 1/2 of pi minus theta, it gives a positive sign. And all of the cosines are positive. You have to remember how to compute this, the directional cosines. Once you know the directional cosines, I just copy these results and we recall the completeness relation. How? E1 prime can always expressed as a linear combination of E1 and E2. And the completeness relation shows that the coefficient is their scalar product. And we know how to compute those scalar products. Substitute them 1, 1 cosine, 2, 1 prime, 2, 1 prime, it is a sine. Okay. In a similar manner, E2 prime can be expanded By making use of completeness relation, I can make a linear combination of E1 and E2. Coefficients are copied. So now we have negative sign. So why don't we make use of matrix representation because it is too busy? Okay, so I'd like to express E1 prime, E2 prime as a column vector. Then this guy, I just copy all of the coefficients in this matrix and flip this E1 and E2 unit vectors as a column vector. So now I know how to convert the original basis vectors into rotated vectors. Okay, now I'd like to find the new components after rotation, after this applying this rotation. After rotating the unit vectors, components will be invariant and only the unit vector has been rotated from here to there, here to there. Then, by making use of the matrix representation of a vector, row vector as a component with the components and column vector with the basis vectors. Now I substitute this value on the right side, substitute in here. And then E1, this is this, and I use this, and substitute in here. Then we have a row vector as Cartesian coordinates and the rotation matrix, and then unit vectors. As I told you, this guy is the same as this guy because the after rotation we have a vector A and it is rotated by angle theta. We have a vector prime, and we can either express in terms of all the components and the new basis and new components with old basis. In either way, the result must be the same. As a result, this one can be expressed in this manner. Okay. Finally, this guy. What's that? This guy in here, column vector. These two column vectors are the same, and these two vectors are the same. Therefore, this guy and this guy must be the same. I have an identity. All right. As a next step, I'd like to express this row vector in terms of column vector. The transformation from a column to row and row to column is a transpose. Now I'd like to take the transpose of these left and right hand side. So this row will stand up to have a column vector. Next step is how can I compute this product, transpose of product? In general, multiplication, after multiplication, if you take the transpose, this is this. In a similar manner, if I want to compute the inverse, if they exist, so their order must be flipped, exchanged. So the proof is already given in the main text. So what I need to do is put this one in here and take the transpose, put this one on the right, and then take the transpose. Transpose is to flip the row into column. This row is transformed into column. This row is transformed into column. As a result, new Cartesian coordinates is expressed in terms of old Cartesian coordinates by multiplying the rotation matrix. You have noticed that these are two. The rotation matrix for the basis vector and rotation matrix for the coordinates, they are very similar but different. They have a relationship that this transpose is this. So this is for the passive, and this is for the active. In physics, we prefer active. Now, we have found that coordinates transforms after physical rotation, and with respect to all the bases, we do not change the basis, keep the basis, then coordinate will transform, and that matrix is this. And we recall the directional cosines. I remember these are actually scalar products of unit vectors. Therefore, what I get is after rotation, I have a prime vector, and this is a multiplication of Cartesian coordinate, new coordinates, and all the bases. And then using this idea, these coordinates are this one multiplied by old one. And this one is this is copied in here. We define the rotation matrix for the active transformation. We keep the basis the same, but we change the coordinates. The result is this form. And if I expand this multiplication, this multiplication, so E1, E2 is here, and this E1 dot E1 prime, E2 dot E1 prime. So this multiplication, multiply, add them up. Okay, and this one, multiply these two and add them up. So E1, E2. We notice, what's that? Using completeness relation, this one is a nothing but E1 prime. This one is a nothing but E2 prime. Aha! From this, we have shown that A prime is invariant whether we use the old coordinate basis vector or new basis vector. But in physics, we prefer keeping the basis and components are varying. That is a very, very important. And in here, we frequently use the completeness relation. This is only for the two-dimensional case. In three-dimensional case, then you have to add this term too.